Welcome to the penultimate week of Newtonian cosmology. Having spent a lot of the course talking really about things which impact the scale factor, the size and shape of the universe, we're now going through actually looking at its constituents. And so we looked last week at dark matter, and this week we're going to actually look at how the other constituents in the universe form. In other words, the elements, the stars, the galaxies, and things like that. And because this is a cosmology course, we're really looking at the universe as a whole. So I'm not going to get into the nitty-gritty of either stars or galaxies, but I am going to talk in broad brush terms about them. And what we actually need to do this is we need to go back to the beginning. We need to look at how the initial conditions in the universe were set. And so these last two lectures are going to be about the early universe. And the early universe is quite a vague term, because it can mean different things to different people. And I'm actually going to split it, rather ridiculously, at about 10 to the minus 12 seconds. So this week, I'm going to talk about things from about 10 to the minus 12 seconds out to about 1 billion years. And next week, the entire lecture, more or less, I think, will be based on what happens in the very early universe at a tiny fraction of a second. And those things are important because they, as I say, they set the conditions of the universe in those very early phases. And they then, of course, run on and have consequences throughout the evolution of the universe. So it's important that we consider those conditions when we run our models of the universe in the future. And so going back now to 10 to the minus 10, 10 to the minus 12 seconds, or something like that, we can start looking at baryogenesis and nucleosynthesis. And the first thing to think of is it's actually kind of awkward to think here about scale factors and densities and things. It's actually easiest to think of this in a certain sense as a thermal history of the universe. So something like, thinking of the universe as having a temperature rather than having a size. And then you can think, when you're talking about things which are more fundamental particle physics kind of things, you can think about temperatures and pressures and densities rather than physical sizes. So early in the universe, we are now well inside the radiation-dominated era. i.e. A is less than about 10 to the minus 4. The universe is about 10 to the minus 4 times smaller than it is today. The redshift is about 10,000 or something like that. And the universe can be thought of as having a temperature. And we know the universe was thermal because the cosmic microwave background is thermal. It's got a beautiful black body thermal curve. It was 3,000 degrees when it was emitted. It's 2.7 Kelvin now. In the early universe, it was even hotter, but it was thermal. And so you can think that the temperature, T, is just going to be proportional to 1 over the scale factor, basically. So you can imagine, if you think about the black body curve, it's just being stretched by the redshift, by 1 plus z, as the thing increases, as the universe expands. It's stretching out. And therefore, the apparent temperature that you observe, or the real temperature, are correlated with the scale factor directly. And so the temperature you can write as being 10 to the 10 Kelvin times the time over about 1 second to the minus a half. And that's just because it's radiation dominated. So if you were matter dominated, that would be, 1 over t to the 2/3 or whatever. So this is a radiation dominated universe, or you can think of this as an energy. So you can write it as kT, where k is the Boltzmann constant, is equal to 1 MeV at t over 1 second to the minus a half. So as time goes by, the temperature drops. These numbers are interesting because these numbers, and MeV, is about the nuclear binding energy of an atom. So you can start doing interesting things with nuclear binding energies at about a second. And I could have started this lecture at a second, but the reason I've gone back a little bit earlier is because I first want to talk about something called baryogenesis. And baryogenesis, very simply, is the formation of baryons. So you might think protons, neutrons, quarks, things like that, things that are normal baryonic matter. And that is very relevant because at some point at this time, you set the following very important condition. And that is the universe is made of matter, okay, plus dark matter plus dark energy, but not antimatter. And it's not kind of obvious why that is, because you can flip all the physics around and do it with antimatter rather than with matter. So why is it that the universe was made of matter and not antimatter? And this was something which happened early on in the universe, we believe, in this epoch of baryogenesis. And actually there's a hint, and that hint actually comes out partly of the cosmic microwave background. And it's in something called the photon to baryon ratio. So today, the energy in photons is tiny compared to the energy in baryons because of the redshifting of the photons. But the number of photons is vastly higher. So in the current universe, the number of photons over the number of baryons is about 10 to the 9. There are about 1 billion photons for every single baryon, proton or neutron, in the universe. Now, early in the universe, we have the following condition. Kt is greater than mbc squared, where this is the mass of a baryon. And then actually you might have baryons being in equilibrium with the photons. In other words, you've got, photon plus photon, and they've got lots of energy, and so they can go through any backward reaction you like. It's a reversible reaction to give you a baryon and an antibaryon. And so at this point in the universe, you should have lots of photons and lots of baryons, and you should have equal amounts of baryons and antibaryons, of matter and antimatter. And so something happens somewhere in this early universe which changes all of that. So sometime in the early universe, you create an inequality. And then you have a tiny number more baryons than you do antibaryons. So you have some efficiency, let's call that eta, which is equal to NB minus NB bar, antibaryons, over the number of photons. So there is a tiny inefficiency of order 1 part in 10 to the 9 that create the universe which is dominated by matter and not antimatter. And that's quite striking. And we don't really know what the details of that are. But something has to break. Some conservation law has to break. And the best bet in town is something called CP violation. That's a particle physics term. So if you think about it, you have to have charge conserved, you have to have lots of other things conserved, mass, energy, and so forth in interactions. But there are several things in particle physics have to be conserved. One of them is charge, and this one's called parity. If you don't know what parity is, it doesn't matter. You will learn that later. But fundamentally, in the product of these things, is not always conserved. So something called CP violation can give you this inequality that you observe here. We don't understand the details of how that works. It's one of the things that's being looked at the LHC and in other places, but it is something which must set why the universe is as we observe it.